Engines equipped with engine brakes have either a 2 or 3 solenoid configuration mounted on top of the rocker shafts. Drillings in each of the rocker shafts connect the oil from the 3 solenoids to the appropriate engine brake rocker levers. When considering 3 solenoid engines, the solenoid between the number 1 and 2 cylinders controls oil flow for brake activation for cylinder number 1. The solenoid between number 2 and 3 cylinders controls oil flow for cylinders number 2 and 3 brake activation. The solenoid between number 4 and 5 rocker levers controls oil flow for cylinders 4, 5, and 6 brake activation. The engine brake has been designed to include a detent rocker lever. The rocker shafts are unique for each half of the engine. With this system, the tip of the control valve locks into the rocker shaft when the brakes are not active. This mechanically locks the brake lever in the neutral position when it is not in use. The designed engine brake double lobe on the camshaft increases the braking capacity by up to 40%. The first lobe on the braking camshaft opens the exhaust valve near the top of the compression stroke. This releases the compressed gas from the cylinder. The second lobe on the camshaft is an exhaust air recirculation event. This opens the exhaust valve near the bottom of the intake stroke. Because another braking cylinder is releasing the compressed air at this same time, this actually charges the cylinder with more air. With more air in the cylinder, more energy is used to compress it, thereby increasing the braking capacity. Additionally, the ECM controls turbocharger speed, boost, and back pressure by positioning the variable geometry turbocharger nozzle ring. The increased boost and back pressure, along with the double lobe of the engine brake cam, all combine to maximize the air charge in the cylinder and make this engine brake the most efficient of its kind. Let's take a look at how the engine brake operates. Engine oil enters the solenoid valve assembly through a drilling in the rocker shaft. When the solenoid valve is turned off, the oil drains back through the solenoid into the overhead. When the solenoid is energized, engine oil flows through the rocker shaft to the brake rocker lever. Engine oil pressure acts against a flat surface area of the detent control valve. This pushes the control valve off its detent position and aligns the slot in the control valve with the cross drilling that goes to the brake piston. The check ball inside the control valve moves off its seat, allowing oil to fill the cross drilling and extend the brake piston. As the rocker lever rotates, the piston contacts the crosshead guide pin. Hydraulic pressure forces the check ball in the control valve to seat. This locks the engine oil in the cross drilling and the piston area. Oil pressure can reach as high as 5,000 psi during a braking event. Any leakage that occurs during the braking event will be replenished when the rocker lever moves off the outer base circle on the camshaft. The check ball will move off its seat, allowing more oil to enter the cross drilling and piston area. When the solenoid is turned off, the spring above the control valve forces the valve back into its detent and locked position. The oil that is trapped in the cross drilling and piston area escapes through the top of the control valve and dumps into the overhead. The engine brake on the X series can be adjusted while adjusting the valves and injectors or separately. To begin the procedure, bar the engine to the A mark. When adjusting the engine brake, the cylinder must have both valves closed and the cam follower for the engine brake must be on the low part of the cam. Push the top of the brake rocker lever down so that the follower makes contact with the camshaft. Loosen the lock nut on the brake lever adjusting screw. Place the engine brake feeler gauge between the bottom of the actuator piston on the brake and the top of the exhaust valve pin on the crosshead. Using a hex wrench, turn the hex wrench clockwise until the clearance is removed. Hold the adjusting screw in position and torque the lock nut to specification. The feeler gauge should have a slight resistance as it is removed. Once the engine brake lash adjustment is made, it is critical that you check the brake running clearance. To check the running clearance, rotate the engine brake lever to the detent neutral position. The clearance between the engine brake lever actuator piston and the crosshead guide pin must be between 20 and 110 thousandths inches. Refer to the service literature for the latest specifications. If the running clearance is not within specification, loosen but do not remove the rocker shaft cap screws. Rotate the shaft in the direction required to get the running clearance within the specified range. Retighten the rocker shaft cap screws and recheck the clearance. It is critical that this clearance be verified on all 6 engine brake levers. If all 3 levers on a common shaft cannot be set correctly, check and replace parts as necessary. Bar the engine to the next position on the chart and continue until the engine brake for each cylinder has been adjusted. Following this chart in sequence allows the rocker levers to be set with a minimum number of engine rotations. The engine brake has its own breakout harness and diagnostic tests in Insight. So let's look at an example of engine brake diagnosis. In this case, we will troubleshoot a complaint of no brake operation. Next, verify that the engine brake on-off switch is in the on position. Disconnect the brake harness from the pass-through connector. Connect the breakout harness to the pass-through connector. With the breakout harness connected to only the pass-through connector, 2 electrical checks can be made: a click test to activate the solenoid, and a continuity check through the circuit from the pass-through connector to the solenoids. The solenoids that are case grounded must ground the ohm meter lead to the block when performing this test. The buttons on the harness provide a signal to activate each of the solenoids from a 12-volt source separate from the ECM. This helps to isolate the cause of a solenoid activation problem. Whenever applying external voltage through this harness to test the solenoids, the ECM side of the harness must remain disconnected to avoid applying potentially damaging voltage to the ECM. For our example, no audible click can be heard from the number 3 solenoid when a signal is sent from the service tool. This indicates that there is a problem with the wiring harness or the number 3 solenoid. When using this harness for continuity checks, do not connect the breakout harness to the ECM. Connecting both sides of the breakout harness results in an invalid reading through the entire brake circuit, including ECM circuitry. Check the resistance between the pin and the breakout tool that corresponds to the solenoid circuit that failed the click test and engine block ground. Finally, check the resistance across the solenoid. In this example, we see that this reading is not within specification and the solenoid must be replaced. The breakout harness can also be used on a running engine. With one end of the breakout harness still connected to the pass-through connector, connect the other end of the breakout harness to the engine brake harness. The ECM actuator supply voltage may be observed by connecting a digital meter between the breakout box and the engine block ground.